All right, welcome. We have chapter 3.8, this thing called implicit differentiation. All right, in pre-calculus, we learned about functions and relations. We've really only worked with functions, where every x value produces just one y value, okay? But we had these things called relations that were kind of like the true backbone. The general idea here is that relations are just sets of ordered pairs, all right? The x values could repeat, and that's fine. All right. So with relations, things like x squared plus y squared equals 25, a circle. All right. We still have graphs. We can still find the slope of a tangent line. Right? If I want this spot right here, I have to know both an x value and a y value compared to this x value and y value, or this x value and y value, or that x value and y value. I have to know the point, all right? But the relation tells us that. If I know this, I kind of know that. And I want to be able to find a tangent line here, okay? I should still be able to do it. We should still be able to take the derivative of this type of thing, okay? So the problem is most of these equations have x's in it, but also y's in the equation, right? It's not just y by itself. Okay, and the y might have numbers, it might have exponents, it might be inside of a sine or inside of a cosine or inside of a square root. Okay, so how do we do the derivative when this happens? Okay, so let's say we have this thing right here, x squared plus y squared equals 25, this circle. To do the derivative of this thing called implicit differentiation, means to do the following. If I want to take the derivative of both sides, the derivative with respect to x d dx, right, we just do the following. The derivative of x squared, well, that's normal. That's an everyday thing we've been doing. That is just 2x. Plus, all right, the derivative of y squared. All right, the things that just have x's are normal, easy, everyday derivatives. All right, but the things that have y and y to a power or anything with y, we just have to do a little bit more. All right, you do the normal derivative. All right, so what would you think the derivative of y squared is? Well, just like the derivative of x squared is 2x, the derivative of y squared, yeah, that's 2y. All right, but since this thing is a y and not an x, we were doing the derivative with respect to x. So technically, we did a derivative of a different variable, all right? So when we do a derivative of a variable that is not an x, we have to do the chain rule, if you remember that. You take the derivative of that variable with respect to x. And I don't know what that is, so that's this dy dx, okay? And we just have to chain that on. It just becomes part of the problem. Now, you could write y prime if you'd like, and that's fine. It means the same thing, but this would be our derivative. On the right-hand side, the derivative with respect to x to a constant, that's 0. All right, so once we're here, the question is, can we do anything to maybe just get this derivative part, this dy dx, this y prime, by itself? Yes, I think we can. I think we can move this 2x to the other side. By subtracting it. We can then divide by 2y on both sides. And that is, in fact, our derivative. So y prime, or dy dx, is equal to, the 2's can reduce, negative x over y. All right, and so if we want the line tangent to our circle at the coordinate point 3, 4, first off, let's just make sure 3, 4 is a coordinate. 3 squared is 9, 4 squared is 16, 9, 16, 25. Yep, that is a coordinate. Okay, so let's find the equation of the tangent line. Y minus the y value of our coordinate equals m, the slope, okay? It's been a while since we did a tangent line. So we have that formula. The m, that's our slope. So our slope will come from our derivative. The x value, negative 3, over the y value, negative 4. x minus the x value, 3. So we can rearrange, we can move the minus 4 to the other side. This is not going to be pretty. We have what? Y equals negative 3/4 x plus 9/4 plus 4. 9/4 plus 4, that's 16/4. All right, and so we have this tangent line. All right, I'm going to go to maybe a Desmo screen and see how this looks. I still have an inverse function right here. All right, so we have x squared plus y squared equals 25. We just said we had equivalent 0.34. Yep, it's on there. Then we said y equals negative 3/4 x plus 25/4. All right, take a look at that beauty. That is a tangent line to our circle. All right, touches at one point perfectly. It's tangent to our circle. And that is, in fact, where tangent came from, that wonderful phrase, a tangent line, tangent to our circle. And the general idea with any tangent line is, again, if you zoom in close enough, all right, your tangent line and your non-straight curve, your circle in this case, do appear to line up. All right, it's kind of how we make straight lines out of non-straight line objects. All right, and that is what we're working on. All right, finding the slope of tangent lines on things that are not nice, good functions, but instead have both x's and y's all in the same equation. All right, so let's do a couple more. Find the second derivative. All right, well, you found the first derivative. All right, so let's do the second derivative. All right, so the second derivative, d2y over dx2 is equal to, well, to do this derivative, it's a quotient rule. Okay, so the derivative of the top, okay, the derivative of negative x is just -1 times the derivative of the bottom, minus the derivative of the bottom. The derivative of the bottom, well, the bottom's a y, so that's like a y prime, times the derivative, the top left alone, over the bottom squared. All right, great. So we have this as our derivative. We can simplify this a little bit. Negative y minus a negative x would be plus y prime x over y squared. All right, so what's weird about this is that in our second derivative, I have y's, that's fine, in this idea of implicit differentiation, but I also have a y prime. Now, what we can eventually do is say, hey, remember that y prime? It was equal to something. So we can take this value of y prime and put it in there. Negative x over y times x over y squared. All right, and we can take what we know for our first derivative and put it into our second derivative where it was. All right, now if we really want to, we can make this look a little bit better. This x would become an x squared. I want to get these two things to have the same denominator, so I can put that over y, make that y squared. All right, and then we can combine those numerators, negative y squared minus x squared over y times, keep that top the same, change this divide to a times, and flip this fraction. And we can get our second derivative. Okay. Now, if we left it like this before I did all that, you would be fine. It would technically be correct. All right, but this one just does look a little bit better when we don't have fractions on top of fractions. All right, so we can do that. But the interesting part is, again, when you take the second derivative of an implicit function, I guess implicit relation, I should say, you wind up having to reuse your first derivative inside of your second derivative, which is kind of fun and interesting. All right, so let's try it again. Another function. We have this wonderful thing. Let's take a look at what that looks like in Desmos. Okay, all right, so we have this relation, not a function, does not pass the vertical line test. All right, and we are looking for the derivative, the slope of the tangent line at 2, 1. All right, so at this spot right here. So I'd expect the tangent line to kind of go up and to the right, down and to the left, right through here. Now it would cross our function again. That's fine. That happens. But right here we would have a tangent line. All right. So the goal is to take the derivative of this thing. All right. To find the slope of that tangent line. All right. So to take the derivative, we're going to take the derivative with respect to x of both sides. All right. So the derivative of each piece, the derivative of 2x cubed, well, that's just nice and normal. That is 6x squared. Plus the derivative of this thing. Well, I do my power rule. 3 times 2, that's 6y squared. But since the variable there is a y and not an x, I have to then chain on a dy dx. All right, I don't know what the derivative of just y is with respect to x. All right, our base derivative is x. All right, minus this derivative. Well, it's a product between two variables. Okay, so I have to do the product rule. The derivative of the first thing. So actually, I'm going to make it a plus and then kind of think of this as a thing. So the derivative of the first thing, the derivative of negative 9x is negative 9 times the second thing left alone, plus the derivative of the first thing, that's a dy dx. Derivative of y is dy dx times the second thing left alone. And then equals the derivative of 0. Well, that is still 0. All right, so we have this very long-looking thing, and it's kind of tough now. We have a lot of variables, a lot of x's, a lot of y's, and two separate spots where I see dy dx. So to find our derivative, our dy dx, we want to try to get just one of those things and get it together, okay? So anything that doesn't have dy dx attached to it, we're going to move to the other side of our equation. So like this 6x squared, I got to move it over. This minus 9y, I've got to move it over. Okay, so I've got 6y squared times, I can call this y prime just for the sake of it. Right, I would still have this minus 9x y prime. But on the right hand side, I've moved the 9y over, so it's a positive 9y. And I move the 6x squared over, so it's a minus 6x squared. All right, you see how these both have this y prime. So we can factor it out from both pieces. Now we get that y prime by itself. Now we just have to move that 6y squared minus 9x to the other side. It's being multiplied, so we will divide. So the top would be this 9y minus 6x squared over this thing, 6y squared minus 9x. Now we could reduce all of these things by 3. 3 goes into 9, 6, and 9 and 6. But if you didn't, not that big of a deal. All right, we want to know the tangent line at 2, 1. Right, so we would plug in 2 for the x's, 1 for the y's. All right, so 3 times 1, that's 3, minus 2 times 2 squared, so that's 4 times 2 is 8. On the bottom, 2 times 1 squared, that's 2. 3 times our x, which is 2, so 6. All right, so we have negative 5 over negative 4. Can make this go positive. And then our tangent line, y minus our y value, equals our slope, x minus our x value. Distribute and move that 1. So we have 5/4 x. 1 is 4 fourths. So negative 10 plus 4 is negative 6 fourths, which would reduce to what? Negative 3 halves. All right, so this would be our tangent line. Five fourths x minus 3 halves. And let's take a look at that, see how we did. And look at that, we did a great job. So our function here, not our function, our relation, all right, at 2, 1, has a slope of 5/4, and our tangent line would be that 5/4 x minus 3 halves. So in general, this implicit differentiation allows us to find the slope of tangent lines, the derivative of non-functions, all right, by just using that implicit differentiation process. All right, a couple more. We have an ellipse, 4x squared, 25y squared equals 100. So to find the tangent line, we take the derivative. All right, derivative of 4x squared, that's 8x. The derivative of 25y squared, well, 25 times 2 is 50y to the first. But since it's a y and not an x, we have to attach dy dx. Derivative of 100 is 0. We get that dy dx by itself, just have to move the 8x over. And then divide by that 50y. We can reduce what? 4 goes into both of those. 4 does not go into 50. What am I talking about? 2 goes into both of those. And we've got our slope. All right, we can plug in 3. We can plug in 8/5. All right, so negative 4 times 3, that's negative 12. 8/5 times 25. 25 divided by 5 is 5. 5 times 8 is 40. All right, so we have our slope, our m there. Y minus 8/5 equals negative 12/40 x minus 3. Now you can distribute and you can get that common denominator. I guess I could reduce this if I wanted to. What goes into 12 and 40? 4, so 3/10. That'll make life easier. So 3/10 times negative 3 would be positive 9/10. Then I have to add that 8/5 from the left to the right. Common denominator times 2, so 16 plus 9 is 25/10. And that could reduce, what, 5 and 5, so 5 halves if I want. All right, let's see what we got on our Desmos to take a look. All right, we were talking about an ellipse. 4x squared plus 25y squared equals 100. All right, so an ellipse. Hopefully you remember doing those in Math 172. All right. In Math 172, I would have told you to divide this by 100 to make this a 1, which means I would divide this by 100 and this by 100. So that would be what? 1 over 25 and 1 over 4. All right, what we learned in Math 171 when you have an ellipse is that the center, all right, there's nothing being added or subtracted with our y or x value, so the center is 0 at 0, 0. 25 is 5 squared, And so the idea is from the center to the right and the left, because it's under our x, should be 5 units left and 5 units right in the center. Great. That was called the major axis, connecting those two. The smaller number 4 is 2 squared, so from the center up is 2, from the center down is 2, and that's kind of how the ellipse gets its shape. We are saying we have a coordinate point 3, 8/5. Yep, right there. And then we have a tangent line. We said -3. Oh gosh, -3/10 x plus 25/10. And look at that. We do have our tangent line. We have checked that. That looks good. A tangent line to an ellipse. What's kind of cool about this, if you got into these things, these conic sections, the ellipse, the hyperbolas, and what they can do for you, the idea that you can kind of rationalize here is, let's say that an ellipse, like the Earth goes around the sun in what's called an elliptical orbit. All right, a lot of things deal with ellipses when you're talking about orbits. So the idea is, let's say that we were flying along on the Earth, going around the sun, all right, and then we maybe release a probe into space. All right, as we release that probe, it's going to follow out on that tangent line, all right, to wherever it is we're going. Now that's not perfect. The sun's gravity would kind of pull it back into a slightly curved shape here, but without that, that's the idea. We would have that you release something, all right, and it's going to go out on that tangent line. I guess better example here would be, you're on a merry-go-round on a train track. I don't know, something that's curved like this shape. If you are right here in time and you are going this way and you release something out the window, you throw a piece of trash out the window as you're curved, the trash stays in that straight line. All right, don't litter. But it would keep following that straight line as it goes, right? Even though you would then start to continue to turn. All right, do we have any more examples here in our implicit differentiation? Second derivative. Okay. So we had our first derivative was -4x over 25y. To do the second derivative, to take the derivative of a derivative, well, we do the quotient rule. Okay, the derivative of the top times the bottom left alone minus the derivative of the bottom, 25y, would be 25y prime, right, times the top left alone over the bottom squared. Y prime we know is this thing, right, and we can reduce a lot. -4 times 25, -100y. -25 times 4x would be positive 100x. Y prime is that wonderful thing over 25y squared. So 25 squared is what? 625y squared. Our x's can combine, our y's and our 25s can reduce, and you can get it to that one big fraction. Right, so I want this to have a y, so that becomes squared. We can then combine those, do the same change flip. So we have -100y squared minus 16x over 625y cubed. All right, so that would be our second derivative. Right, and then one really important idea with this, and this is really where kind of our applications start to go. Our next chapter in this course are the applications of derivatives. And it kind of involves a lot of these things. So we have, the volume of a cone. We can find the volume if the radius is 4 and the height is 16. That's easy. Volume equals 1/3 pi times the radius squared times the height 16. Okay. So the volume here would be what? 16 times 16. That's what? 256. So 256 pi over 3. About 268. Well, it didn't even tell me my units, so I did a terrible job writing that problem. So about 268 units cubed. That's great. So if the volume has to stay the same, but the radius and the height are allowed to change, okay, find out how those two things change in relation to each other. Find the dH/dr. Okay, so the volume has to stay the same. Find dH/dr. So take the derivative of your height with respect to r. All right, so the derivative of a constant is going to be 0, always. Okay, but the derivative of this thing with respect to r, that's like dy dx, take the derivative with respect to r. So r is the variable, it's kind of like my x. H is more like my y. So to do this derivative, that's a product. These two things are multiplied, so I have to do the product rule. I'm going to treat these three as my normal, and then this is my first, and then my second. All right, so the derivative of the first with respect to r is my variable. So 2 times 1/3 pi is 2 pi over 3 r times the second thing left alone, plus the derivative of the second thing, the derivative of h with respect to r, is just that, the derivative of h with respect to r times the second thing left alone. All right, our goal is then to get this thing by itself. Okay, so move this to their side, this 2/3 pi r squared. Sorry, 2/3 pi rh, and then we've got pi r squared over 3 times dH/dr. So I would multiply by 3, and that'll cancel that. I would divide by both sides by pi, and that would cancel that. And I'd move the r squared to the other side by dividing. And r squared and r would reduce. So I've got negative 2h over r is my dH/dr. Right. So find the rate of change of the volume, okay, dH/dr, when r is 4 and h is 16. So plug in 4, plug in 16. So negative 2 times 16 over 4. So negative 32 over 4 is negative 8. All right, which means as our equations are changing here, if the volume has to stay the same, all right, I'm sorry, the rate of change of the volume, that doesn't make sense. That shouldn't be of the volume. Find the rate of change when r is 4 and h is 16. Basically, this means the rate of change of the height with respect to volume. Means if I increase my r, if that r has to get bigger to keep the volume the same, that means the height is going to have to get much smaller, much quicker. Okay, so this should be, find the rate of change when r is 4 and h is 16. Okay, So in order to keep that constant value, if the r is going to get any bigger at all, that means I'm going to need a very, very sharp decrease in our h. Okay, that -8 for an answer there means that for my r to change just a little bit, I need a very large negative change in height. And that should make sense. If I want to keep the same value and my r gets wider, if I have a wider cone, the cone's going to have to get a lot shorter. All right, that width matters a little bit more than the height when it talks about value. Okay, if I have a smaller radius, it means my r is going to get smaller, then my h is going to have to get much bigger, all right, to accommodate for it. It is not a proportional radius, it is proportional change there. But that relationship there, when r is 4 and h is 16, is -8. A small change increase in r is going to make a big decrease in height of that cone. Right, and we do a lot more of this. If that was super confusing, I'm sorry. We do a lot of this in the next module, and we talk a lot more about it. All right, but applications of these derivatives, how variables are changing in relation to each other, is going to be a big topic. All right, but implicit differentiation in general, the general idea, things that are just x's, you take normal derivatives. Things that have y's in them, you take the derivative like it's an x, but then you have to chain on that dy dx. All right, and then you generally try to solve the equation for dy dx. Get everything else to the other side, and only dy dx is on the first side. All right, reach out with any questions, and good luck.